Hey everybody, this is the team Way to Secant, and we are going to be talking about Ann's theorem for Math 3021, Section 501, and I am Christine Lindsay.
I'm Carrie Anderson.
And I'm Benjamin Goff.
So to get started, we're going to discuss what Ann's theorem actually is. So we're going to let P be a point inside the convex quadrilateral ABCD, which a convex quadrilateral is when all four interior angles measure less than 180 degrees. It has two diagonals, and the diagonals are inside the figure, such that ABCD is not a parallelogram. In the case that ABCD was a parallelogram, then E and F would lie on the same point, and this theorem would not be used. So to continue on with Ann's theorem, we're going to let E and F be the midpoints of the diagonals AC and BD. And then we're going to draw the line that connects P to each of the vertices. And then if the sums of the areas of the opposite triangles are equal, then P is going to be located on the line that connects E and F. So a little bit of the history of Ann's theorem. It was named after French mathematician Pierre-Léon Anne, who was alive from 1806 to 1850. This theorem itself tends to be fairly unknown concerning the convex quadrilateral. Many people don't actually know what this theorem is, and usually when they do see it, it's just through different geometry books or articles that they'll see that this theorem, but it's not usually used in the everyday. And then it's also not very known onto how he discovered it or proved this theorem. Due to the timeline that he was alive, this theorem kind of doesn't make sense as to how he put it in place and how he discovered why it should exist. And then the Newton line did already exist at this point, but the usefulness and the definition of this line became more clear through this theorem.
So in order to prove Ann's theorem, we will need a few lemmas. So first, we're going to start by proving that vertical angles must be equal. So a line is defined to have a measure of 180 degrees. So then two angles that span that line must have measures that add to 180 degrees. So for example, if AEC had measure x, then we would know that AED must have angle measure 180 minus x. Then we also know that BED must have 180 minus 180 minus x. And by some simple algebra, we find that BED is also equal to x. Therefore, angles AEC and BED are equal, so vertical angles are equal. So next, we're going to talk about a congruency criteria for triangles. So two triangles are congruent if roughly they have the same size and shape. More specifically, that means do the two triangles have all three sides being the same and all three angles being the same. But we don't actually need all six of those quantities to be equal to show that two triangles can be congruent. So let's say, for example, we have two triangles with two pairs of equal angles and the side between them as equal as well. Now, what we're going to do is slide point A onto point X such that AX or AB, of course, lies on top of XY. Now, we know since AB lies on top of XY, and we have given that AB is equal to XY, that means we know points B and Y coincide. Next, we will say, since angle AC, ABAC is equal to angle YXZ, then we know that line segment XZ must lie on top of AC. And now we know that C must coincide with Z. For example, if they did not coincide, then we would know that the angle B and angle Y would be different, which we cannot have. So we know that C and Z coincide. And since all 3 points coincide, then by definition, all 3 side lengths are equal and all 3 angle measures are equal. So then we have shown that the two triangles are congruent. So a similar criteria that we can use is the AAS. Now, the key difference between this one is the two triangles have two pairs of equal angles and the side outside of those two angles are equal. So what we know is that the sum of angles inside a triangle must sum to 180 degrees. So then we know that angle C is equal to 180 minus the sum of angle A and B. And since A and B are equal to X and Y respectively, then that sum, that quantity is equal to 180 minus X plus angle X plus angle Y, which is by definition the angle of the measure of angle Z. So then we have shown that angle C equals angle Z. And since the two triangles have equal angles with the side between them as equal, then this is exactly the scenario that we had in the previous slide, and we can use ASA to show that these two triangles are congruent. So now we're going to show that perpendiculars from a line to its bisector must be equal. So let's have two lines intersect, lines AB and CD intersect, such that CD bisects AB. In other words, the intersection point E is halfway between A and B. So AE equals AB. Now we're going to draw the perpendiculars from A to C and B to D. So assume AC is perpendicular to CD and BD is also perpendicular to CD. Then what we know is angle ACE is equal to 90 degrees and angle BDE is equal to 90 degrees. So those two angles must be equal. Now we know the vertical angles AEC and BED are equal, as we showed earlier. Then we know that we have two angles as the same and the side outside of them is the same. So then this is exactly the scenario to use AAS. So these two triangles, ACE and BDE, are congruent. Then since the triangles are congruent, then each corresponding side and angle are equal. So we know that the corresponding sides AC and BD are equal. So then we know that the perpendiculars from a line to its bisector must be equal.
Another important concept we will need is the area of a triangle. The area of a quadrilateral, such as this rectangle, is base times height. We will let K represent the area, H represent the height, and B the base. Therefore, the area of the rectangle is K equals B times H. A rectangle has 4 right angles, so by drawing a diagonal, we will get 2 right triangles. Clearly, each triangle is half the area of the original shape. This gives us the equation K equal to 1/2 base times height. Besides a right triangle, we will also have to consider 2 other cases. The first is an acute triangle. Given an acute triangle, draw one of its altitudes and let it connect with BC at point X. This creates 2 right triangles, ABX and ACX. Since we already know the equation for the area of a right triangle, we will use this to solve. Area of a triangle ABC is equal to the area of triangle ABX plus the area of triangle ACX. This equals 1/2 BX times H plus 1/2 CX times H, ultimately giving us the area of ABC equal to 1/2 BC times height, or 1/2 base times height. The second case is an obtuse triangle. Drop an altitude from one vertex to a point outside the original triangle and extend YZ to meet it at point P. This gives us 2 right triangles similar to the last case, larger triangle XYP and smaller XZP. Subtracting the smaller from the larger gives us the area of XYZ equal to 1/2 base times height. It follows that the area of any triangle is equal to 1/2 base times height. Now that we have all the necessary pieces, we'll move on to the proof of Anne's theorem. First, we'll start by showing that if P coincides with either of the midpoints, E or F, then the sum of opposite triangles will be equal. In this image, opposite triangles are represented in the same color. First, draw heights of triangles ABC and triangles ACD, and label them H1 and H2, respectively. If P coincides with E, then P is the midpoint of line segment AC. Then the area of triangle ABP is 1/2 AP times H1. Since P is the midpoint of AC, AP is equal to CP. It then follows that the area of BCP is equal to 1/2 CP times H1, which is also equal to 1/2 AP times H1, which ultimately gives us the area of triangle ABP. Similarly, ADP is equal to 1/2 AP times H1, and CDP is equal to 1/2 CP times H1. Therefore, the area of triangle ADP is equal to the area of triangle CDP. It then follows that the area of ABP plus the area of CDP is equal to the area of BCP plus the area of ADP. The same follows for if P coincides with F.
So now that we've shown that the area of ABP plus the area of CDP equals the area of BCP plus the area of ADF, we can take a look into the line that actually connects E and F. So we're going to draw the quadrilateral ABCD, and then we're going to place the point P right in the inside of that convex quadrilateral. And so then we're going to represent AC and BD as the diagonals of this quadrilateral ABCD, and we're going to note that E and F are going to be the midpoints respectively. From earlier, we're going to go ahead and connect point P to the different vertices. Earlier, we talked with Ben about the perpendiculars that bisect. And so since F is the midpoint of BD, it's going to bisect EF. So the perpendiculars H from line BD onto the bisector EF are equal. So ultimately, we have PF being the base and H being the height. So what we're going to see now is that the area of BPF is going to be equal to DPF, as well as the area of APF is going to equal to CPF. Again, this was due to earlier when Ben discussed the heights being equal. We can prove that these triangle areas will be equal as well. Furthermore, we're going to see that the area of APB is equal to AFB plus the area of APF, as well as the area of DPC is going to be equal to area DFC minus the area of CPF minus the area of DPF. And we can see that represented here with these shaded triangles. Ultimately, that gives us the area of APB plus the area of DPC is going to equal the area of AFB plus the area of CFD. Next, we'll see that the area of APD is equal to the area of AFD plus the area of DPF minus the area of APF, as well as individually, area of BPC will equal the area of BFC plus the area of CPF minus the area BPF. Ultimately, we can conclude from those two statements that the area of APD plus the area of BPC equals the area of AFB plus the area of BFC. Furthermore, we can finally conclude that the area of AFB equals the area of AFD, and that the area of CFD equals the area of CFB. Lastly, we get from those two equations, those two equalities, that the area of APD plus the area of BCP equals the area of APB plus the area of CPD. So, since we have showed that the area of APD plus the area of CPD of BCP is equal to the area of APB plus the area of CPD. And ultimately that P lies on the line EF. So then we can see that since P lies on that line that connects E and F, this line is ultimately known as the Newton line.
So the Newton line is the line that connects the midpoints of the two diagonals of the quadrilateral with at most two parallel lines. So if the quadrilateral is convex and it's not a parallelogram, then the two midpoints would not coincide. So if we draw the line between them, we call that the Newton line. So some interesting findings relating to Ann's theorem is actually Newton's theorem as well. So Newton's theorem states that if a circle can be inscribed within a quadrilateral, then its center must lie on the Newton line. So Newton's theorem is a direct result from Ann's theorem. So we can actually use Ann's theorem to prove Newton's theorem. Now, similar to Ann, Newton's findings and his proof for his theorem are unknown. We don't have evidence that he showed it. So many questions arise whether to see if Newton's theorem, whether he was first to actually discover this, or whether he needed Ann's theorem, or it was just on his own. So questions concerning how it was proved before the time of Ann also come into play. So the Newton's line, which is the special straight line that was defined earlier, has an unclear connection to the two theorems because of the timeline. And then for our sources, we sourced a lot of our history from the University of Debrecen in Hungary. And for the definition of the Newton line, it came from Wikipedia. And some acknowledgements. Our professor is Dr. Akbar at the University of Texas at Dallas for the class Math 3321, Section 501 in the spring 2021 semester. And that concludes our presentation.
Thank you.